In a previous video, we derived the equations of motion for the 2 degree of freedom system shown here. This consisted of two masses, m1 and m2, connected to each other with a spring of spring constant k2, and then mass 1 was restrained to the wall with a spring of constant k1. And the equations of motion are as shown on the right, which we'll call number 1. In this problem, we'd like to look at the unrestrained problem, also known as the semi-definite or degenerate problem. And the idea here is what happens if we cut the spring from the wall, the spring K1. I'm going to begin by duplicating this diagram. Okay, and then what we will do is effectively set K1 equal to 0, which is the equivalent of just deleting that. And I will say that here that, K1 is equal to 0, and that K2 would be equal to K in this case. All right. And when we do that, the equations of motion become m1, 0, 0, m2, x1 double dot, x2 double dot, and then the K matrix will simplify to 2K, excuse me, not 2K, just K, minus K, minus K, and K, and then this vector is x1, x2 equals 0. 0 vector. And we'll call these equations number 2. Okay, and then we proceed as we usually do, where we assume a solution of the form. We know it's a simple harmonic motion, so we can say that x vector of t is equal to some vector that we'll call x naught, x initial, times sine of omega t plus phi, where we know from before that omega will be the natural frequencies. We call this number 3. Therefore, taking the second derivative of this, exactly as we've done before, x double dot of t is equal to minus omega squared times x of t. Call that number 4. All right, and if we substitute 3 and 4 into equation 2, we get minus omega squared m1, should be squared, m1 minus k, and minus, I left out the plus k here, minus omega squared m2 plus k. And that is times x1, x2 equals 0, 0 vector. That would be equation 5. And then as before, we know that for non-trivial solutions, we know that the determinant of this matrix must be 0. So we write that as follows, minus the determinant of minus omega squared m1 plus k, minus k, minus k, minus omega squared m2 plus k is equal to 0. Let me make some more room here. We're going to take this up here. Back to black. So we multiply the diagonals, we subtract the product of the off diagonals, we get that minus omega squared m1 plus k times minus omega squared m2 plus k. Minus k times minus k is k squared, so we subtract k squared equals 0. If I expand that, I get omega 4 times m1, m2 minus omega squared m1k minus omega squared m2k, and then I get plus k squared minus k squared. Those cancel, so this is just equal to 0. I'm going to take out omega squared as a factor, and I get omega squared times omega squared again, m1, m2 minus m1k minus m2k equals 0. So either omega 1 squared is equal to 0, which would obviously imply that omega 1 is equal to 0. We'll call this equation 6. Alternatively, omega 2 would be the other natural frequency, and that would be equal to the square root of k into m1 plus m2 divided by m1 times m2. Take the square root of that. We'll call that number 7. Excuse me, this is, yeah. And let me make an assumption that if m1 is equal to m2 is just equal to m, so both masses are the same, this implies that omega 2 is equal to the square root of 2k over m. That's what that would simplify to. We'll call that equation 8. So again, what we've done is we've gone ahead and cut this restraint. We have a semi-definite problem. Why is it semi-definite? Because in addition to mass 1 and mass 2 vibrating, oscillating with respect to one another, there's also the ability of this system to act as a rigid body and to translate. Probably a good real-life example is the case of two train carriages that are linked together with some coupling that has some elasticity to it. So if you can imagine the two train carriages in a certain mode of traveling can travel together down the track. Alternatively, they can oscillate, they can vibrate back and forth with respect to one another. Those would sort of be the two modes of operation. And the reason that I'm presenting the semi-definite problem, other than to show you how to do it, is it actually, in my point of view, gives a lot of understanding as far as what are mode shapes, what is the solution we're coming up with in terms of vector notation, what is a basis, what do we mean that these mode shapes are orthogonal. So we're going to explore that a little bit. But fundamentally, the important thing to note is that in a semi-definite system, one of your frequencies is equal to 0, meaning the system can move without vibrating, and this is a result of it being untethered. All right, let's continue. So what I've done is I've gone ahead and reproduced the diagram. I've made the point that we said K1 and K1 is 0, K2 is K, and M1 and 2 are the same, they're equal to M. And I want to compare this to the single degree of freedom system. In the case of the single degree of freedom system, you might remember that the natural frequency is root K over M. Okay? In this case, I'll rewrite it, but just to go back here, the natural frequency is root 2K over M. Okay, that's interesting. So it doesn't really behave like a single degree of freedom system, even when these two are just vibrating. It actually vibrates somewhat quicker. So to that point, let me rewrite the equations of motion. Well, I've rewritten it here for you, but let me come up with the results, and that was omega 1 we found was equal to 0. We call that equation 6. And we also found that omega 2 was equal to 2k over m square root. And that's approximately equal to 1.41 root k over m. So this will oscillate approximately 1.41 times faster than the case of the single degree of freedom system. That might be interesting to some of you. Right, now let's have a look at the mode shapes. This is exactly as we did before. Mode shapes. And this is from equation 5. Just write that in here. So because the determinant is 0, both the equations are actually the same equation. Right? We've explained that in a previous video. I won't elaborate now. So we can pick either one of them. I'm going to pick the top one, which says that minus omega squared times m plus k times the coordinate x1 minus k times x2 is equal to 0. Call that number 9. Rewriting it, we can write it in terms of x2 as x2 is equal to 1 over k times minus omega squared m plus k times x1. We'll call that number 10. Right. And then we can pick one of them because these equations are not, well, they're linearly dependent. They're not linearly independent as a result of the determinant being 0. That's the way we set it up. We've got to pick one of these values and then calculate the other one. So arbitrarily, I'm going to pick x1 to be at 1. Call that 11. Okay, let me just make some more space here. All right, let's look at mode 1. Mode 1. So if I take equation 6, which is the frequency omega 1 equals 0, if I take 11, which is that x1 is equal to 1, and I substitute these in to equation 9, or equation 10, I should say. Then what I find is that x2 equals x1 equals 1. So my first mode shape, which I'll denote as phi1, is equal to 1, 1. We'll call that equation 12. And I'll come back to that. Let's just calculate mode 2, and then we'll come back and talk about what these mode shapes are telling us. So mode 2, this requires using the second natural frequency, this one we calculated here. I didn't put an equation number next to it, although I did previously. This is equation 8. And so what we want to now do is take equation 8 and 11, and substitute those into 10. And we find that, what's the easiest way to do it? I'm just going to write it as x2 is equal to 1 minus m over k times omega 2 squared times x1. Okay, we know that x1 equals 1. I'm just going to cancel that. Okay, and we substitute for omega 2 squared. We end up with, I can lose the parentheses, 1 minus m over k times 2k over m. The k's cancel, the m's cancel. I end up with 1 minus 2, and that is equal to minus 1. And so therefore mode 2, we'll call it phi 2, phi sub 2, is equal to 1 minus 1. So the 1 mode is when both coordinates displace the same amount. Phi1, for every 1 unit that x1 displaces, x2 displaces 1 unit. Well, what would that be? That would be the rigid body motion. It's basically saying that both masses move together by the same amount. That would be the rigid mode, and we know this, excuse me, because we know the frequency is equal to 0 in that case. The second mode is one where for every 1 that x1 moves, x2 moves 1 unit, the same amount, in the opposite direction. So you can imagine this mass moving this way and mass 1 moving the other way, or vice versa, and it's just a pure oscillation. So we'll find out in a second that depending on the initial conditions, in other words, how you set it into motion, you can either excite one mode or the other mode, or in general, a combination of the two modes. So if we set it into motion where we gave mass 1 and mass 2 exactly the same velocity, we would expect this just to move down the track as a rigid body. On the other hand, if we set mass 1 and mass 2 in motion in opposite directions, we would expect there would be no rigid body motion, and basically the middle of the spring here would stay in the same place, and masses 1 and 2 would just oscillate backwards and forwards with respect to one another. Okay, I know that's kind of wordy, but I think if we move on, it will become a little bit clearer in the next slide. So what I've done is I've gone ahead and copied the results here. This is our semi-definite system. We know that the one mode shape is phi1 is 1, 1. We know that that frequency is 0. That corresponds to the rigid body mode, also known as the degenerate mode, because the frequency is 0. Anytime you hear degenerate, you should be thinking to yourself one of the frequencies is 0, and therefore it moves as a rigid body, or it has the ability to move as a rigid body. All right, so now what does this mean? I've got this question a lot. What exactly is a mode shape? What does it mean that a mode shape spans a space? Well, let's consider a few things. In the event that we had an x and y axis, typically you would say your x-axis looks something like 1, 0, right? You're moving in the x direction but not in the y, and similarly the y-axis would be 0, 1. We know in the case of the x and y axis, this spans a space, meaning anything within this xy plane that I've drawn could be written as a linear combination of these two basis vectors, these two vectors. Okay? I say it's so much in the x direction and so much in the y direction. Another way of saying it is it's a certain amount, let me just use u and v in this case. I could say any position, any point, P, is equal to U in the E hat X direction. E hat is exactly this unit vector. I'm just using shorthand. It's commonly written as E hat, plus V in the E Y direction. We also know orthogonality holds. What does orthogonality mean? Before you tell me it means they're at 90 degrees to one another, yes, of course they're at 90 degrees to one another, but in a more general sense, two vectors are orthogonal when their dot product is 0. So we know that E hat x dot E hat y is equal to 1, 0 dotted with 0, 1, which equals to 0. Okay? Are our vectors, our mode shapes, phi1 and phi2 orthogonal? Well, why don't we take the dot product? Phi1 dotted with phi2 is equal to 1 minus 1 equals 0. So they're orthogonal. So you should think as phi1 and phi2 kind of like your x and y unit vectors. Anything, any motion within this system can be written as a linear combination of phi1 and phi2. In other words, a certain amount of phi1 and a certain amount of phi2. What actually determines that are the initial conditions of the system. All right, let's see if we can explore a little bit of that mathematically here. Let's try to make a bit more space so I can keep it on this page. Okay, so as the final point in this video, let's go back to the equations of motion. We remember that we assumed a result in the form of x of t was equal to x, some vector x naught, sine of omega t plus phi. And we actually found out there were two results. There were two omegas, right? The two natural frequencies. So in fact, this could be written more as some constant, which I'll call C1, times what do I want to call this? Phi1 times sine of omega t plus phi. omega 1t plus phi 1. I should put in there. Plus, for the second result, c2 times phi 2 times sine of omega 2t plus phi 2. And I'm realizing that I actually don't want to call these phi because I've used phi for my mode shape, so I'm going to make this a capital phi. This capital phi is the phase difference. Okay? Not to be confused with these small lowercase phis up here, which are the mode shapes. Okay? Probably not the greatest notation. I apologize for that, but that's what it is. Right? And that's the idea, is that I can further go ahead and substitute our known values. We'll say that this is equal to C1 times phi 1 times, we know omega 1 is 0, so this is just sine of capital phi 1, plus, and then the second term remains the same, C2 lowercase phi 2 times sine of omega 2t plus phi 2. Oh, let's put in what omega 2 is. Omega 2 is 2k over m square root times t plus phi 2. Okay? So what are our unknowns here? We don't know, let me check it off. Here are our unknowns. We don't know what C1 is. That's a constant which comes out from the initial conditions. We don't know what C2 is. And we don't know the capital phi 1 and phi 2. So there are 4 unknowns. In order to determine this, we use the initial conditions. I'm just going to write them as ICs. And one of the conditions looks something like, we know the position of each mass at time 0. We'll say that the vector x is known at time 0, and it's equal to x10, x20. And we also know the derivative, or the velocity, at time 0 is equal to x dot 10 and x dot 20. And to be clear, even though there are 2 initial conditions, each one of these initial conditions is actually 2 equations. The first one tells you something about x1, and the second one tells you about x2. This is 2 equations, and this here is actually another 2 equations. So we have 4 equations and 4 unknowns. And as I mentioned before, the nature of these are going to be such that based on the initial conditions, the response, x of t, is going to be a linear combination of this, which is actually constant, it's not time dependent. That would be the rigid mode, where both masses don't oscillate, but they move together, plus this oscillatory term, which has to do with the natural frequency times time. So the idea here, and I find the semi-definite cases a lot easier to imagine, it illustrates it better for most people, is that anytime you have a system like this with, say, 2 degrees of freedom in this case, the system wants to oscillate in one of its 2 modes, its 2 natural modes. There are 2 different ways that the system wants to oscillate. And any motion of the system can be written as a linear combination of these 2 oscillatory modes. That's what we mean by the mode spans the space. That's also what we mean by any response can be written as a linear combination of the modes. But for some reason, I find people find it easier to grasp when one of these modes is a rigid body mode, because it's easier to imagine it as a combination of, hey, it's moving together as a rigid body, and separately, it's vibrating with respect to one another. But that's what you should get out of these mode shapes here, that they're orthogonal. In that sense, they behave very similarly to unit vectors, like your x and y axis. And as a result, and based on the initial conditions, any motion within the space can be written as a linear combination of the 2. Okay, that's all I want to say about this problem. Feel free to ask questions if anything is unclear. I hope you found something of value out of this, and if you have, please go ahead and give it a thumbs up. That way other people will get to watch it too. Thanks for watching, and we'll see you in the next video.